This is project 3 video number 1, the one in which we do the pencil and paper part. We got two particles, particle 1 and particle 2, each having a magnetic dipole moment, one at the origin point in the plus x direction, and particle number 2 at x, y, pointing in with its magnetic dipole moment pointing in the theta direction. Alright, let's get a sketch of that. So I got put a coordinate system on here and put a particle with the magnetic dipole moment. Call that particle number 1, so it's got mu1 as its magnetic dipole moment, and then another particle up here. I call it particle number 2, the magnetic dipole moment mu2, and it's making some angle theta with the plus x direction. And this is the position vector of particle 2 with respect to particle 1, and the coordinates for that number 2. It's x over and y up. So let's see. We got to find the force being exerted on 2 by 1. That force is given as F is equal to the magnetic dipole moment of the victim times dotted into the magnetic field, and we need the gradient of that, so I'll make a little more room. The gradient of mu2 dotted into b1. So let's start getting the pieces. Mu2, we can draw a little vector component diagram for mu2. Looks like mu2 oriented at an angle of theta, mu2x, mu2y opposite over hypotenuse is equal to the sine of the angle, so mu2y is equal to mu2 sine of the angle, and mu2x is the adjacent divided by the hypotenuse, would give the cosine of the angle, multiply both sides by mu2. Then we get that mu2x is mu2 times the cosine of theta. So mu2, the vector, is mu2 magnitude cosine of theta times I hat plus mu2 sine of theta times j hat. Alright, I think we're going to need that later on. Definitely going to need it. Then B1, the magnetic field due to particle 1 having being at the origin, having a dipole moment of mu1. The formula for that is given on your formula sheet, where we have mu0, the universal constant, divided by 4 pi times 3 times the magnetic dipole moment of the particle that's causing the magnetic field dotted into r hat. A unit vector in the same direction as r. That green R that we've got up there. This vector R. And then times R hat minus mu1 itself, the magnetic dipole moment of particle number 1, all divided by R cubed. Alright, so we need mu1 to put into there. Mu1, alright, it was just pointing in the positive x direction, so it's going to be mu1 magnitude times I hat. So let's try plug in what we've got in there. Oh, we're going to need R hat, and we need R. So first off, the vector R is x times I hat plus y times j hat. In other words, to get from particle number 1 to particle number 2, you go x along the plus x in the plus x direction and the distance y in the plus y direction, so it'll be x times I hat plus y times j hat, which is just what I wrote. And the magnitude of that, R mag, is square root of x squared plus y squared. I'm going to just keep calling that combination R as much as I can wherever I see it, rather than replacing it with the x squared plus y squared. But we know what that is, and it's easy to calculate based on given values. It's supplied by the user, the x and the y. Alright, I need R hat. Unit vector in the R direction is R divided by its own magnitude. This is what I mean. I'm going to call that just R. So R hat is x over R times I hat plus y over R times j hat. Alright. What else do I need, if anything, up here? So this is, I need mu1. I've got right here mu1, R hat, mu1, and R. Yep, I think I got everything I need to plug into my expression for B1. The given formula, the one on the formula sheet. Alright, so B1 mu0 over 4 pi times 3 times mu1 is mu1 I hat dotted into R hat, which is x over R times I hat plus y over R times j hat. And then once I do that dot product, it gives me a scalar, and it's multiplying the vector R hat. Then minus mu1 times I hat. And all of that is being divided by R cubed. The R hat, I think I would like to go ahead and substitute for that. So R hat, this should be right now, is x over R times I hat plus y over R times j hat. And there's the R hat, and then minus mu1, and there's the mu1 times I hat. Alright, that's more like it. So now let's go ahead and do the dot product. So B1, the vector, times 3, and then I got I hat dotted into I hat gives me 1, so that'll be mu1 x over r, and then I hat dotted into j hat gives me 0. So this whole thing in the square brackets is just mu1 times x over r, which I've already written down to keep that in the square brackets, and multiply that by my old r hat, then minus mu1 I hat. All of this is over r cubed. Alright. So now, vector B1 equals, I'll just go ahead and distribute this. So 3 mu1 x squared over r squared x is not cooperating, x squared over r squared times I hat plus 3 mu1 xy over r squared times j hat, then minus mu1 over I hat, all divided by r cubed. So B1 equals, looks like there's a mu1 in everything. So I got mu 0 over 4 pi mu1. I'm going to gather the i's together, so without the mu1 I've got 3. And I'll divide this into here, so that'll be an x squared over r to the 5th. So the mu1's been factored out, divide that in there, and then minus 1 over r cubed, all times the I hat. And then plus for the j part, remember the mu1 I already took out. So I got 3 xy, and then over r squared, all divided by r cubed, so that'll be over r to the 5th. Now our force is the gradient of mu2 dotted into B1. So let's find mu2 dotted into B1 for now. So mu2 dotted into B1 is what? Well, we found mu2 up here a while ago. mu2 cosine of theta times I hat plus mu2 sine of theta times j hat. times j hat. Dotted into what I just found. Times yeah, this looks like an R sub 3 there. I'm going to write that. Make it look more like an R cubed, which is what it's supposed to be. Alright. I hat plus 3xy over r to the fifth. And that, I got a vector here, and that's not a vector, so I must have left something out up here. The 3xy over r to the fifth was supposed to be multiplying j hat. Right there, that came from that piece right there with the mu1 factored out. So that's times a j hat. See if that looks right. So I want to go ahead and do the dot product. So it's a vector here, and we're dotting them together. Mu2 dot b 1 equals, I'm going to have this, in this first piece I got the I dotted into I is going to give me 1, and then it's all that stuff multiplied together, including the mu0 over 4 pi times mu1, and then times mu2 cosine of theta, then times this stuff in the parentheses. Alright, that gives me the first part, and then plus this I hat dotted into j hat gives 0, j hat dotted into I hat gives 0, so the next one that gives me something non-zero is the j hat dotted into j hat. So everything that's multiplying there, I got the mu0 over 4 pi mu1, and then times the mu2 sine of theta, and times the 3xy over r to the fifth. And the j hat dot j hat was just 1, so pure number there. I'm going to simplify this, I'm going to define there's some constants out here like mu1, mu2, theta just given by the user, mu0 a universal constant, and this whole thing is another grouping of constants, so I'm going to call this grouping of constants A, and I'll call this grouping of constants to, I think I'll take it with the 3 as well. In fact, I'll pull that 3 out front. So it's 3 mu0 over 4 pi times mu1, mu2 sine theta. That'll be my B. And then I can write this expression for mu2 dot b1 more simply as a times 3x squared over r to the fifth minus 1 over r to the third plus b times xy over r to the fifth. Alright, the a and the b have the same units as each other, and then in here I've got units of 1 over length cubed, or dimensions of 1 over length cubed minus 1 over length cubed. So that works good. And then over here, length squared over length to the 5th. So again, 1 over length cubed. So the dimensions are working out. The units are going to be right. So now it's time to get the force. The force is the gradient of mu2 dotted into b1, which is the derivative of mu2 dotted into b1 with respect to x times I hat plus the derivative with respect to y of mu2 dotted into b1 times j hat plus the derivative with respect to z of mu2 dotted into b1. Now, that r's got an x squared plus y squared in it. I got an xy, x. We can see that the derivative mu2 dot b1 doesn't depend on z. So these are actually partial derivatives. When I take the partial with respect to x, that means hold y and z constant. When I take the partial with respect to y, hold x and z constant. When I take the partial with respect to z, hold x and y constant. Well, if x and y are constant and it doesn't depend on z, the whole thing is a constant, so that derivative just gives 0 because no z dependence. So f sub x is the little piece that's multiplying the I hat, so that's the derivative of this dot product with respect to x, the partial derivative. So in other words, keeping the y and the z constant. Keeping the y constant since z's not in there. So let's go ahead and do that fx then. It's the derivative with respect to x of this whole thing up here. I'll write it as a times 3x squared r to the minus 5th minus r to the minus 3rd plus bxy r to the minus 5th. And I'm taking the derivative of that whole thing. So fx is equal to, it'll just be a times the derivative of this thing in the parentheses. And this thing in parentheses has two terms. The first one is a product, so it'll be 6x times r to the minus 5th, and then plus the 3x squared left unchanged times a minus 5 r to the minus 6, but times dr by dx using the chain rule for that last part. And then minus, I need the derivative of this piece, that'll be a minus 3 times that with the power reduced by 1 times the derivative of the inside dr by dx, and they should be partials. And then plus. Alright, this piece has the y I can treat as a constant, so I'll say it's by times the derivative of the rest of it. The rest of it is a product, x times r to the minus 1/5. So I'll take the derivative of the first piece times the second one. And then plus the first piece left alone times the derivative of the second. Bring the minus 5 down. Then times that to the power reduced by 1. R to the minus 6. And then times the derivative of the inside, which is dr by dx. So we're taking the derivative with respect to x. Alright, I think that's got it. That's fx. So fx equals, so we can simplify this a little bit. I think I'll go ahead and write that as 6x over r to the 5th plus, it's a minus 15. X squared over r to the 6th dr by dx, and then plus 3 over r to the 4th dr by dx, and then plus b times by times 1 over r to the 5th minus 5x over r to the 6th dr by dx. This is this dr by dx. There should be one in there as well. So I think I'll pop it in there. That was a dr by dx. That's not fitting so well. Let's make it so that the dr by dx is outside of that, and I think that'll make it so I don't need this. So I took the derivative of this whole thing with respect to r, and then multiply that times dr by dx, and that works. So dr by dx. Alright. That is f sub x. Let's get rid of the dr by dx. R is equal to the square root of x squared plus y squared, which is equal to x squared plus y squared to the minus 1 to the 1/2. So dr by dx is going to be equal to, I bring down the 1/2, times x squared plus y squared to the power reduced by 1, and then times the derivative of the inside with respect to x, that'll be 2x. So the 2's cancel, and I get dr by dx is equal to x over square root of x squared plus y squared, which is x over r. So I'll substitute x over r in for dr by dx. It makes fx be a times 6x over r squared minus 15 x squared over r to the 6 times x over r plus 3 over r to the 4th times x over r plus by times 1 over r to the 5th minus 5x over r to the 6th times x over r. And I think I'll try to simplify that a little bit more. It's fx equals a times, I have a 6x over r squared. I don't think that looks right. Let's see if that's a copy error right there. That should have been r to the 5th. Yeah, let's fix that up a little bit better. Let's see if the rest of it makes sense. So 6x, I think I got an r to the 7th, and I got another r to the 5th right there. So I've actually got 6x plus 3x over r to the 5th. So that'll be 9x over r to the 5th minus 15x cubed over r to the 7th. And then plus by times x over r to the 6th minus 5x squared over r to the 7th. And I got to fix up a correction that I made up here. I had that r to the 5th without being multiplied by that, and it was actually right. I was just taking the derivative with respect to x here, the first factor, which gave me 1, and then times r to the minus 5th. So this dr by dx should actually only be multiplying the second term there. So let's restore that back to the way it was, which was correct, and adjust that change throughout. So it's multiplying that one. I think it's just a matter of moving this out here now. Alright, then same thing for this. Move the bracket out. got it. Over here, move the bracket out. And this needs some erasing, then. That's 1 over x to the 5th. 1 over r to the 5th. Alright, I think I fixed that up. Let's see, dimension-wise, this be 1 over length to the 5th, 1 over length to the 5th. This is 1 over length to the 4th, and 1 over length to the 4th. So these two are consistent with each other. Oh, and then the y out front is concerned. That makes the whole thing 1 over length to the 4th. Now, these two big ones are consistent with each other, so the dimensions are okay. I think that does it for getting fx. So let's work on getting fy. Fy is the derivative, partial with respect to y, of mu2 dotted into b1. If I can find that up here someplace, mu2 dotted into b1. There it is. A times 3x squared over r to the 5th minus r cubed. A times, I think it was 3x squared something. Wow, maybe I should try. I'm gonna look at it where I had it in here. So, right there. Okay, I'm going to copy it down in this form right here, but put a d by dy in front of it, and it's going to be fy. Alright. So, let's do Control Z here. Put d by dy. Of a times 3x squared r to the minus 5th minus r to the minus 3rd, and then plus byx r to the minus 5th, all with respect to y. So it'll be a little bit simpler because the x is being held constant here. So for this first part of it, I've got a, and then the derivative with respect to r. I think I'll go ahead and do the whole thing in parentheses with respect to r. So there'll be a 3x squared times minus 5 r to the minus 6, and then minus a minus 3 r to the minus 4th. So I've taken this the derivative with respect to r of this first piece, and then I got to multiply that times dr by dx, and then plus, alright, this one has a y in it, so I'll take the derivative with respect to y of the first factor. That'll just give me bx r to the minus fifth, and then plus the first part left alone, so bxy, alright, I changed the order a little bit, times the derivative of the second part, which is going to be minus 5 times r to the minus 6 times dr by dy. I think got to straighten that out. That's dr by dy. I'm taking the derivative with respect to y this time. Partial. So let's simplify that a little bit. That's a times minus 15. I'll go x squared over r to the 6, and then plus 9 over r to the 4th. All times dr by dy plus bx over r to the 5th plus minus 5 minus 5 bxy over r to the 6 dr by dy. Alright, dr by dy. R is equal to x squared plus y squared. I think it's going to be y over r. To the minus 1/2. Nope, to the plus 1/2. So, just the square root of x squared plus y squared. So dr by dy is 1/2 all this to the minus 1/2 times the derivative of the inside with respect to y, which is equal to y over square root of x squared plus y squared, which is y over r. So dr by dy is equal to y over r. So we can substitute that in, and we get a times minus 15x squared over r squared plus 9 over r to the 4th times y over r, and then plus bx over r to the 5th minus 5bxy over r to the 6th times y over r. We're getting there. This is f sub y, as I recall. Yeah, let's put that in there occasionally. So f sub y equals, I'm going to multiply that y over r through a times, I'm going to call it 9y over r to the 5th minus 15x squared y over r cubed. That's not looking too good. The units aren't working out there. So r cubed, how did that 15? That's right there. That's r to the minus 6, not r to the minus 2. So we're r to the 6th there. And times r makes it r to the 7th. I think dimensionally that's going to work out better for me. And then plus, you could go a b, factor out the b in both of those terms, and go, I wonder if I want to factor out a bx. Yeah, I could have factored out an ay there, so I think I'll just keep that in there. So I will factor out a b though. X over r to the 5th minus 5 xy squared over r to the 7th. So dimensionally, I got 3 there, 7 there. 1 over distance to the 4th, 1 over distance to the 4th, 1 over distance to the 4th, 1 over distance to the 4th. Yeah, it's actually easier to have that x in there, so for comparison, probably should have had that up here. Let's see if I actually want to change that. This was fx. If I put it'll be more consistent if I put the y in both of those. I need a y there and a y there. Alright. So now, all I have to do is say, I got fx and fy. The magnitude is equal to fx squared plus fy squared. And the angle, we got fx plus fy the angle is the arctangent at fy over fx. I gotta tell you though, with the possibility of this f pointing in any direction, I could have an angle down here where both fx and fy are negative, and the ratio of them, instead of getting what I would want, which would be this angle when I take the arctangent of it, I'll just get the same thing as this angle when these guys are when it's pointing in the exact opposite direction to what I got there. So it has to do with the fact that the arctangent is multi-valued, in that there are to get the same value when you take the tangent, there are multiple angles that will give you the same value. Any angle plus another 180 degrees gives you the same value. So what the Octave has built in is a special function called atan2, I think. Theta equals atan 2 of f of y. And it's something like that, because I think in this case the answer will be in radians. So I think I'm going to have to look that up when I get to coding it. But beyond that, we're pretty much ready to go. So I need the outline of the code. I needed mu0 in there. Well, I'm going to say the arguments of the function are whatever we were told they had to be. It was a theta, it was mu1, mu2, and I got commas in there. This one, there we go. So those are the arguments, so they're passed to the function. Code outline. Then I gotta initialize, I gotta plug in what mu0 is, tell it what mu0 is, and then A equals and B equals from above. Calculate what those things are. I think I got, if we scroll back there, you'll see it's mu0 over 4 pi times mu1, mu2 cosine of theta 1. Actually, let's take a look, see if I get that right. I think I put it in blue, so it should jump out at me. Mu0, mu1, mu2 cosine of theta all over 4 pi. And the other one's more or less the same thing, except I got a 3 out front, and it's a sine of theta. So do you want to put, yeah. And then this one is 3 mu0 over 4 pi, mu1, mu2, sine of theta. It looks like theta 1 there. It's just a theta. Alright, so then I think we're ready to calculate what fx is. Or just, yeah, I think we got everything that goes into fx. Let's make sure. So where's fx? There it is. Let's get a copy of that down. Alrighty. So I said fx is equal to a times 9x over r to the 5th minus 15 x cubed over r to the 7th, and then plus b times y over r to the 5th minus 5x squared y over r to the 7th. And then copy down what fy is. Seems like I just found that. So 9y over r to the 5th minus 15 x squared y over r to the 7th. Multiplying a. I think it's 9y over r to the 5th minus 15 x squared y over r to the 7th. So same as up here, except one of the x's in each case gets replaced with a y. And then plus b, and let's see what we got up there. X over r to the fifth, and xy squared over r to the seventh. So that actually looks the same. X over r to the fifth minus 5 x squared y over r to the seventh. Let's see if that. No, xy squared, so it is different. The second one is different. Both of them are different. xy squared. Okay, here it's as if one y got replaced with an x. No, the x and the y got reversed. And one of the x's got replaced with a y. Alrighty. Then calculate f equals square root of fx squared plus fy squared. And phi, I think I'll call it. Phi is equal to a tan 2 of fx comma fy. I think times 180 degrees over pi. So this gives me the right idea, and if the details aren't quite right, we can fix that when we're doing the actual coding. And yeah, I shouldn't have called that theta. We already had a definition of theta, so let's fix that up. That's a phi, phi, and a phi. And the units are working out right. This business here, like on here, x went to y, one of the x's went to y. Here, one of the x's went to y, and then the only oddball thing here is this a y went to an x, as far as comparing the two things. But the units look like they're consistent. Let's see, while I was taking the derivative of with respect to y, how that came about. So yeah, the y went away and all there was an x, whereas when I was taking the derivative with respect to x, the x went away and all there was a y. And then this extra y here came about from the derivative of r with respect to y. That was y over x, whereas in the other case it was x over y. So I think things are making sense. It looks like the units are working out. Seems dimensionally consistent. So this is my code outline. Get those arguments, initialize that variable. I got to look it up, what mu0 is, and plug it in, and then express, get a value for A, a value for B, and then here it's all plug in. Oh, I have skipped one step. R. We used R as well. Alright, there we go. That should fix that up. I got something for R, so I calculate the A, I calculate the B, calculate the R, and X and Y were supplied by the user, so then it's just plug in, and from there on out I think I got exactly what I want. So let's call that a wrap for project 3 video number 1.